So, do you usually do Rob's job for him, or?
I don't have to. I can't fix all the bugs in Rob's code.
Hey guys, welcome to Embedded Toolbox, the video interview series where we try to save the world by solving one engineering challenge at a time. And one of the topics that we've addressed on Embedded Toolbox in the past is the use of tools, static analysis tools in particular, but everything has its limitations. Static analysis is not by any means a perfect solution. So we've brought on Yannick Moy, who's the product director for Spark. Your product manager, right?
That's okay. Yeah.
Okay.
No problem. I can be director. Yeah.
He's just got a promotion. Um, he's
Okay.
he's the product manager for Spark over at Adacore. How are you doing today, Yannick?
Very fine. Thanks, Brandon.
Um, So, like I said, we use static analysis tools widely, especially in safety and security critical industries and applications, automotive, aerospace and defense, industrial, etc. But like I said, it's not a perfect solution. What's beyond static analysis? What do you need to do in addition to that in certain use cases, and why?
So that's exactly what our customers feel when they go to our solution with Spark to approve programs. So when you need guarantees, is where static analysis is usually not the dream solution. Static analysis is very good at finding problems and usually easy problems.
Mm,
It will stop in two ways. First, it will not give you all the problems that it finds because it wants you to find problems that you can solve. So problems where there's an easy solution, where you won't bang your head against the wall to understand the problem. And second, it won't allow you to go beyond a list of messages where you have to triage and find the solution by yourself or accept the message from the setting analysis tool. So for these two reasons, there are tools that go beyond, that are more powerful, but that also require more interaction with the user. And Spark is one of these. And one of our customers used to say, Spark starts where static analysis tools stop.
So you mentioned proofs. Can you explain really quickly, for everybody's benefit, what a proof is and why it's necessary beyond, your typical static analysis?
So proof is really about giving guarantees, being certain that you don't have certain kind of problems. So just imagine buffer overflows.
Mhm.
Static analysis tools will search for possible buffer overflows that have an impact on your program. Proof will guarantee you that there are no buffer overflows in your application. So if you are the kind of application that really requires the program to keep running, don't stop, don't allow an attacker to chime in, then proof might be a solution for you.
Very good. So we're going to actually harken back to a previous interview we did with one of your colleagues, Rob Tice,
Yeah.
who's working with a platform called the Spark ZUMO here on Embedded Toolbox, and had a codes and had a little code base, and he ran the code peer static analysis tool against that code
Yeah.
base to try and find various errors. And you're going to take us a step deeper. Is that right?
Yeah, so I'm going to look at the same code snippets with Spark and show you that you can go beyond what it did with code analysis.
Very good. Let's dive right in.
I'm looking at the same code that my colleague Rob Tice showed in the previous edition of the Embedded Toolbox using CodePeer to detect problems. And so you can find it on GitHub. And I'm looking at the exact same pieces of code. So here on this piece of code, Rob showed that static analysis was complaining about a possible division by zero. And so I can launch the Spark tool on just see this program here. So let's launch it at a small level. And Spark will report here the possible division by zero. So the fact that we're looking at arrays of short integers here, and while they might be zero if you don't have more information. But it also reports a number of other problems. So here there's arithmetic involving floating point numbers, and there are a number of problems that may occur, not only division by zero, but also typically overflows. So you might overshoot. This function argten, well, you might expect it to be similar to the mathematical argten and give it a meaning so that when it returns, you can multiply this by a quantity and not overflow, but you need to provide this information. And there are ways to provide this information. So if we look here at this function readMag, so this is calling a function that has a precondition. So here, this is a condition that should hold before you call this procedure. This is just a Boolean here that should be true so that it checks that things are properly initialized. So when we go back at this call, the tool informs us that it cannot prove that this precondition holds, and it suggests we add it as our own precondition for this function. Indeed, here we are checking that this unit is initialized, but not that the other one on which we're making a call is initialized. So we should say here that this ZUMO lsm303.initd is initialized. So this boolean is true before we call. And if I look again at this line, so let's prove just this line. We can do that with the interface. And here it says that the precondition is proved. So we have helped the tool figure out that the code is indeed correct. And the tool has the nice property that it really looks one function at a time. About the same as when you're doing a deep code review.
So really quickly here, Yannick, is Spark a tool or a language subset of Ada, or what are we dealing with? Is it both?
It's both, yeah. So because we want to be able to apply these very powerful tools, we have to subset the language. And not too much. It's just a bunch of restrictions on what you can do with all of the features. So you cannot use concurrency unbounded. You cannot use object-oriented unbounded. You cannot use pointers unbounded. You have bounds on every one of these big features. But mostly you have all of Ada, and in particular on these Spark ZUMO codes, I didn't have to do any modifications to use Spark, because also my colleague had Spark in mind when he created the code.
Very good. And then a second question is, all right, so let's start comparing this to what we would have seen if we were just using static analysis. You know, we have this this bottom half of the user interface here, and if you're using a static analysis tool, it's raising a bunch of flags, but that's about it, right?
Yeah. So it really doesn't give you more than possible errors, and then you have to triage and go figure out if you can change the code, or if you have to accept these messages and say it's okay and validate that. With Spark, you can really go back to the code and either add specifications or help the tool figure out that it's correct. So there's an interplay, there's an interaction here between the tool and the human to make sure that the code is really correct. So we can see that even better with the second example that Rob showed. So here there's another function which does some computation and does some averaging out of our window. So again, I can just call quickly the proof on just this subprogram. And here what static analysis showed is that when you were accessing this array, there was a possible array out of bounds. So buffer overflow in language like C. And here it says exactly the same, that the values here for the average should be within the bounds of this array. So you can see here in Ada it's an array, and you should have these coordinates, x coordinate and y coordinate. Now, if you look at the codes, you can see that these averages are first summing in this x sum and y sum of a loop, and then dividing by the size of this window range. So you expect the average to be within bounds because these fields here have exactly the right coordinates. And you can try harder with the proof tool. So now I can ask to prove at a deeper level of proof, using more provers, giving more time to the tool. And that gives indeed more powerful results. It's still not the end, so you can still go beyond. So for example, on this small loop, I saw that there are still things that are unapproved. Well, I can just ask just for these parts to go at a still higher level of proof. And here I ask that it reports what it managed to prove, so we can be sure that, like before, so here the overflows. So I don't overshoot the integers that I'm using in this computation. So there was still issues here. So let's ask the tool to report what were the remaining issues. So here there's a window index, which is used to access in this window array. And indeed, the tool says, well, that might be out of bounds, and you should check. So why there's a check? To explain the syntax and semantics, you should check when you access an array that the value is within bounds. It even suggests a fix like before, so that this procedure filter state, which we're analyzing, has a precondition that says that window index is small enough. And it's the same problem for this part of the post condition, is window index within bound. So we could add a precondition here, but the other way is just to refine the type. So in Ada, I could say that this window index is really in the right range. So between 1 and window size, it doesn't have any reason to go beyond. So now if I rerun the tool, so let's ask for a bit more power. So now it has the right range for window index. So we expect this to go through. And maybe everything is proved. So let's see.
So, do you usually do Rob's job for him, or?
I don't have to. I can't fix all the bugs in Rob's code. So here there's a problem. There's a remaining problem, and this second part of the post condition here says, using this tick all attribute in Ada, that Windows index, the new value, should be different from the old value. So you should have updated it, and that's what occurs in this code. So if we click on the magnify icon, we can see a trace of what's happening here. So with window index 1, it doesn't change value. Why here? Because if we take the state's value unknown, it just takes the first of these branches in this case statement, similar to a switch in C. And so we're not updating window index. So this post condition really is wrong. So either the code should be updated, or the contract that there's a mismatch here that the tool has pinpointed. So that's all. But
Wow.
I hope that I showed you these tools are really engineering tools, and that's what we see with our users. That you need no math degree to use these tools.
That's great. So I just want to make it clear, are you using now Spark on top of a static analysis tool, or is it completely distinct and separate?
Yeah, that's completely different. So it's a different family, different world of static analysis tools. Static analysis like CodePeer, like the main use of static analysis tools is tools that go through your code, rummage around, and try to find bugs.
Mhm.
Here with Spark, we're really looking at a small window of code at a time, typically what you would do with reviews. And here the tool can really translate that to state-of-the-art provers and call all of these provers, and you have a swarm of provers under the hood that go around and try to prove your properties and give you strong guarantees that indeed the code is as you intended.
Mhm. There's a huge installed base of C code and other assembly, etc. So what happens if you're dealing with something that you really need proved, but you already have a ton of infrastructure built in another language?
You replace part of it. So you replace the critical part.
Mm.
Uh, it's really hard to get to the same degree of assurance with C codes, both at the human level. You know that there are a number of issues in C code that are even more difficult to review in humanly than with Spark or Ada code,
Hmm.
but also at the tool level. So it's very hard to have a tool that does that for C or C++ code, almost impossible. And so if you need to get these guarantees for the subset of code that really needs to work correctly, then what people do is that they replace parts of the code, the real core important part of the code, and you can grow from that. So Spark and Ada can be compiled to the same targets as C code, and you can link C and Ada code together if you use the same compiler, GCC, for example. Or if you have a target for which there's no GCC compiler, you can generate C code from Spark and Ada using our common code generator. So there's a number of options, and we have users who do all of that.
Obviously, there's the other part here, which is, are you telling me that I got to learn a new language?
Yeah, well, these days it's expected, right? Software engineers have to learn new languages. So here it's not only for fun; it's also because there's a true advantage if you need to get correct code. And so if you want to learn about it, it's all available online on learn.adacore.com, both for Ada and Spark. And for Spark, you have these small code editors. So I can really write in it, and you can play with it. So you can call the prover inside the editor, and it really reports the messages on the code that you've modified. So it's all there.
Wow. So for everybody in the audience who's watching, I'm going to throw a gambit down. If you can take Rob's code, throw it in here, and find any more little bugs or vulnerabilities or anything in his code and send them to me, I'll send you one of those one of the Spark ZUMO bots that he was using in the first episode. That's a deal.
Great. Rob is gonna love it. Oh, and if you want to go beyond what this interface offers, especially if you want to analyze the Spark ZUMO code, you want to download the Spark plus NAT Community Edition on our website. So
Very
if you
good.
want to really get the board.
Right. Yes. Yes. Here
And the bots.
we're doing everything we can to help you get one of these boards.